Hello, and welcome to Pulse 2014. Today we're going to talk about software-defined environments from IBM. When we talk about software-defined environments, we're really talking about next-generation automation for cloud, bringing application-aware, resource-smart software to your data center for optimized infrastructure at the physical layer and at the virtual layer in your cloud. We're doing this through the use of patterns and policy-based orchestration of your workload and infrastructure, and using analytics to drive this optimization of all of our software-defined resources. Let's talk about the architecture of software-defined environments. It comes in three tiers: lifecycle management, operational management, and infrastructure management. When we talk about lifecycle management, we're talking about defining the workloads and the applications that we want to run on our infrastructure. When we talk about operational management, we're talking about how do we bring those patterns and those workload definitions to our infrastructure, and how do we manage and monitor the health of that over time. And then infrastructure management is all about optimizing our physical and virtual resources, bringing virtualization to our compute, storage, and networking, and managing the bare metal resources that we're using to host all of our applications. Today, we're going to look at two demo scenarios for software defined. First, we're going to talk about DevOps. When we talk about DevOps, we're talking about the ability to manage the lifecycle of our applications through a very strict set of interfaces and processes in order to ensure that we get high quality development, test, and production of our applications. Software defined contributes greatly to this by providing very consistent infrastructure and runtimes to host our applications. The second demo for software defined we'll look at today is all about elastic infrastructure. This is where we start bringing in our policy and automation for our infrastructure to help make sure that we meet the service level agreements for our applications. We'll look at a big data workload that we're running on our software defined environment, and how when we aren't making our service level agreements, we're able to automatically scale out the physical infrastructure and rebalance our virtual infrastructure in order to ensure that we meet those service level agreements. We've got Platform Resource Scheduler providing policy to help us automate the virtual workload balancing, and GPFS with file placement optimization ensures that our data stays close to the compute resources. So software-defined environments, right? We've talked about this idea of automation and how we manage our infrastructure, both the physical and virtual, and how we're defining patterns and managing the lifecycle of our applications, right? We've got all these pieces and parts to play. When we bring all these things together, we really want to bring this extreme automation to all of these different processes and all of these different personas that are acting within the software-defined environment, right? So on the infrastructure management and control plane side, right, through the technology that we're building here at IBM, we're able to dramatically reduce the amount of time and hands-on effort that is required to provision our physical infrastructure and apply our control plane to it, right? How do we get OpenStack and all of our software-defined storage and networking enablement for that? And then we've got tools like Urban Code Deploy and Smart Cloud Orchestrator to help us on the operations and lifecycle management side. Today, we'll look at how all of these three things come together in order to provide a fantastic software-defined environment. So the first thing we'll look at today is how software-defined environments behave for the operations team. To do this, we're going to go into Smart Cloud Orchestrator and take a look at how we can build out our infrastructure and application patterns to deploy our workloads. We're going to look at our production credit card processing application to do this. We've got part of our pattern already defined, but we need to add additional resources to it. We'll start by adding in additional compute resources, and then we got to define what applications we're going to run on this. To do this, we're going to pull in components from Urban Code Deploy that have already been defined from Urban Code. So here we'll pull in our Big Insights controller for our Hadoop middleware, and then we'll add in our application, our credit card processing application, our production version. We can also pull in additional infrastructure components, add floating IPs so that we have external internet access to access our applications, and we can even bring GPFS Cinder volumes on board as well. Here we're going to be able to choose from our GPFS file system types, right? We've got fast and slow storage. In this case, we want a high performance development workload. We bring in GPFS fast. How much space we want to use and how we want to mount that onto our system so that our application can take advantage of it. That's it. This is some of the things that we can do through our pattern development in order to take advantage of our software-defined environment. Now that we've defined what our workloads look like, let's go ahead and deploy them. Before we get started, we're going to configure our Platform Resource Scheduler policy management tools that are controlling the provisioning of virtual infrastructure in our cloud. By default, all of our clouds use a CPU load balancing policy. However, for our development cloud, we want to switch to a packing policy. This policy change, it means that we'll be densely packing our virtual resources onto the minimum number of physical resources possible. This means efficient use of our cloud resources that are being provided to us by software. Now we'll go ahead and deploy our applications. What we're doing now is deploying the patterns that we defined earlier via Smart Cloud Orchestrator. These patterns are going to be transmitted as hot documents, an OpenStack standard for defining virtual infrastructure workloads. In addition, we've got integration with Urban Code Deploy so that we can deploy application components as well, all through the heat engine provided via OpenStack. Using these open standards means that we're easily able to leverage the community resources that are available here as well. Today, we're using our own custom-built patterns, but we could leverage those from the community as well. Now we'll move on to lifecycle management using Urban Code Deploy. Lifecycle management is all about managing the versioning and quality of the applications that you're running in your environment. Now, previously we deployed those patterns from SCO, our operations management tool, and as a result, those patterns have full integration with our lifecycle management tools with Urban Code Deploy. Here we can see all of the virtual infrastructure agent systems have been automatically registered with our Urban Code Deploy server, and we can see all of our applications have been deployed automatically to those systems. Now, we've heard that there's some issues with the credit card processing application that we've got running out in production, and in order to go do the development and test processing of that, we're going to go ahead and start with our dev environment. So to do that, what we want to do is deploy a new version of our credit card processing application. The Big Insights middleware is fine, so we continue along with the same 1.1 version, but here we'll switch over to version 2.0 of the credit card processing application. All we need to do is go ahead and select that new version, hit OK, and then submit that, and Urban Code Deploy will take care of the rest for us. Now, once we've completed the deployment of this, we would go ahead and run this through our typical test processes in our development environment, and once that's completed, then we can go ahead and roll it out in production, which we'll do next. So you can see now in our development, and we're running version 2.0 of that processing application. It's checked out from our test team, and we're going to go ahead and deploy the same thing out into production. The key here is that with software-defined environments, we can expect consistent results across all of our dev and production environments because of software-defined. It means we've got common standardized interfaces to all of our infrastructure and runtime so that there are no surprises when we go from dev to production. That's it. We've completed the deployment, and now we can see that both our production and development environments are both running at version 2.0. This is fantastic. It was super easy for us to go ahead and manage the lifecycle of these applications after we deployed out into our environments using our operations tools. Now let's talk a little bit about infrastructure management. This is really important, right? So for your data center administrative staff, they've got to have some way to provide this software-defined environment to your consumers, right? Your operations team and your lifecycle management team. How do they build out these patterns and workloads and get them deployed onto the infrastructure, right? They need a standardized platform in order to do this, and they're going to build these hot documents to pass into the infrastructure to define their workloads and get them running. But what do they pass it to? Well, we're using OpenStack as our platform, right, for our virtual infrastructure. But how do we turn physical infrastructure into virtual infrastructure? Well, today we'll use Platform Cluster Manager Advanced Edition in order to do this. Really straightforward and simple, right? We've got cluster definitions defined for our OpenStack clouds. And this includes the ability to automatically scale out our physical infrastructure to expand the capacity. First, what we'll do is deploy out onto software for our development OpenStack cloud. And that's it. We just select the number of systems and off it goes. It's a really straightforward process to be able to get new clouds stood up. Now we're going to deploy our production cloud onto our on-premise environment. So we go ahead and give it a name. We tell it we want to use 2 physical systems. And that's it. We go ahead and create that cloud. That's it. It was that easy for us to stand up 2 brand new OpenStack clouds with Platform Cluster Manager Advanced Edition. One on SoftLayer for development and one on-premise for our production use. Not only does this include the OpenStack control plane, but it's also leveraging SDNVE for virtualized networking and GPFS for hyperconverged shared storage, as well as Cinder-backed persistent storage for our virtual instances that we'll deploy. Our deployment's complete. Let's go take a look at our OpenStack clouds that we've provisioned. Here's our on-premise cloud. We can log in real quick and see that there's no virtual workload running on this yet, but that will change, right? Earlier we went through Smart Cloud Orchestrator to do the deployment of workload, and we'll see how that impacts our clouds in just a moment. We'll also take a look at our OpenStack cloud on software as well. Looks identical. No workload running on it, but the important thing to note here is that it's bit for bit identical to our on-premise cloud. Now we want to take a look at the control plane, right? This is IBM OpenStack with our Nova, Cinder, and Neutron drivers for GPFS, SDNVE, and KVM. This also includes Platform Resource Scheduler. We'll see how that comes into play here shortly. Let's take a quick look at the workloads that we deployed earlier from Smart Cloud Orchestrator. From an OpenStack standpoint, it's got a complete view of this workload, right? It's not just a huge pile of individual pieces and parts. This means that your cloud administrators can really see how these workloads are being deployed by your operations team, and they can see the relationships between these things. Not only the infrastructure like the compute, storage, and networking resources, but we can also see the application components that are included in that pattern as well. Here we can see the networks that have been provisioned as part of those hot documents. And finally, we can take a look here and see that because we're using Platform Resource Scheduler and using the default CPU load balancing for our production cloud, we can see that the virtual CPU load is spread evenly across our two hypervisors. We'll notice here that we're overcommitting and we're well beyond the base availability of virtual CPUs that match up with the physical infrastructure, and this will come into play later on in our demonstration when we talk about elastic scale-out of our infrastructure. We can go over to our development cloud on software, and we can see that our credit card processing development application is here as well. Same view, same infrastructure that's supporting this. It's really nice for your cloud administrators to be able to see how the infrastructure they're providing is being leveraged by the consumers. Now we'll take a quick look at the hypervisor utilization here in our production cloud, and we'll notice that one of our hypervisors is entirely idle and one is being used 100%. This is because of that choice we made earlier with Platform Resource Scheduler to do stacking on our development cloud. What this means is that we can use the minimum amount of physical resources in order to host our virtual applications that are being used by our development team, keeping costs down. Now let's run a little workload and see how our cloud responds. We're going to run a TerraSort benchmark on this system, 300 million rows, and we're going to see that that's going to finish in about, 10 to 12 minutes or so, I think, here for that to complete. Now, what happened in the back end is that Platform Cluster Manager is actually monitoring that physical infrastructure and that cloud that it provisioned, and it sees that CPU utilization and memory utilization have grown considerably, and it knows that based on the policy we define that we really need more physical infrastructure to support that cloud than we've already got. And as a result of this, it's going to flex up and add additional compute resources automatically to that cloud. This process is fully automated based on our cloud definitions that we provided earlier to PCM, and now we can see that our cloud is active once again. And if we go back to our OpenStack console, we can see that we've now got 3 compute nodes as part of our cloud, and we're rebalanced this virtual CPU utilization. So now we're at 100% utilization for all 3 of our compute nodes. All of this has happened fully automated. The consumer of the cloud had no idea that anything changed. Sometime later, after the cloud has expanded, he's going to run his same workload again. And as a result of that, right, his processing is going to be considerably faster. He didn't do anything to change his application, but we're getting better utilization of our physical resources now with additional resources brought on board automatically. This is a really powerful way for our cloud consumers to operate. They just know that they expect a certain amount of service level to be available to their applications, and the infrastructure that supports it through software defined is fully automated, going to scale out the amount of resources available to make sure that our workloads are meeting their service level agreements. Fully automated on both the back end and the front end. That's it. I want to thank you for taking this time to watch our demo around software-defined environments. You can come see us out on the show floor. We're in the Infrastructure Matters booth number 460. Thanks.